like I said about a week ago, we are about one lecture ahead of the schedule, okay? And doing this lecture today on matrices sort of gives you a little bit of a head start on the the Mobius for week 6, because remember there's no lectures, there's no tutorials in week 6, but there is Mobius, okay? There is Mobius. So I thought we could do a little bit of this today and just introduce you to the topic. It's not a very big topic, right? And my personal view is that when they were putting this course together many, many decades ago, they're like, oh, let's just throw something about matrices in there. That's my professional opinion. Okay, so this stuff, it's not massive in terms of content, and you will get some flashbacks from 1231, Math 1231. Okay, so the algebra in Math 1231. So Math 1231 is sort of, we're kind of taking quite a few ideas from that, from the algebra, and we're going to use it to do some stuff. Okay? So, a couple of things first, right? What's a quadratic form? Well, we're going to be looking at these things in 2 dimensions. Okay, so what's an example of a quadratic form? Well, something like this. X squared plus 3xy plus y squared. Okay? So it's a polynomial in 2 variables and the degree or the order's 2. Okay, so, you know, you can check that by just saying, oh, each term, the powers in each term have to add up to 2. Okay? So that's a quick check. Now, we're actually going to use matrices to look at these special quadratic forms, okay, and learn things about them. All right, so let's just briefly remember or revise what basic matrix theory is. Okay, I won't spend a lot of time on this, right? So I'll just make a couple of notes. Suppose you've got a matrix A, and it's a square matrix, right? Can anyone remember how you diagonalize a matrix? Are we bringing back bad memories here? Yeah, you're on the right tip. So definitely, sort of. So what we're trying to do is take that and make a nice diagonalized matrix. So you've got just numbers sort of down the main diagonal and zeros everywhere else. So yes, similar. So let me post it. So you want to form like this, right? So I don't know, you've got lambdas down here, and zeros everywhere else. Okay? So that form down the left-hand side is called a diagonal matrix. But before we answer the question, why would you want a diagonal matrix anyway? Does anybody know?
It's symmetrical.
Yeah. Yeah, and it's pretty simple. Right? It's only got entries down like one diagonal and zeros everywhere else. Now, zeros are simple to deal with, and so are these diagonal matrices, right? So let's say this is my D for my diagonal matrix. So how do we do it? Well, we definitely use the inverse, but before we do that, we say form the eigenvalues and the eigenvectors of this matrix A. Okay? So to do that, we solve some equations, and then let's say you've got so let's say the eigenvectors are this. Let's just say you've got two of them. Okay, so I'll show you how to compute eigenvectors in a minute. Just let me know that that they're just columns of this new matrix P, and what you then do is you say, okay, that's my P, so P inverse AP equals the diagonal matrix. Okay? Now it's okay if you've forgotten all about this, I'll go through it step by step, that's fine, but I'm just giving you a general introduction here. Okay? Now, for our kinds of matrices that we're going to deal with, they have a special form. Okay? So, such that the matrix and the transpose of the matrix are the same, okay? Can anyone remember what is the transpose of a matrix? What do you do to get to transpose something?
Is it when you flip the y rows in the columns?
Yeah. Yep. You're basically switching column 1 with row 1, and you're switching column 2 becomes row 2, etc. Right? Okay, so back to these quadratic forms. I can write this in the following way. Okay, 1, 1. Okay. So basically, I've got this quadratic form written as through vector and matrix multiplication. Okay, so all I've done is I've put the coefficients of the squareds down the main diagonal, and then I've halved the other coefficient, the 3, out of the 3xy, and put it in the other, sort of the anti-diagonal, if you like. Okay? So, have a look at this one. If I transpose it, do I get the same matrix? All right, so that row becomes that column, yeah. That row becomes that column. Yep, it's the same. Okay? So for these special so-called symmetric matrices, come just at the right time. Yeah, just getting into the matrices. So for these special symmetric matrices, the eigenvectors and the eigenvalues are predictable, and this P matrix is also nice, this P matrix, because the inverse of P is the transpose of P. Let me say that again, okay? For these so-called symmetric matrices A, all the eigenvalues that we'll learn how to calculate, they're all real valued and they're all distinct, they're not the same, okay? All the eigenvectors are orthogonal, right? But for me, what I think's most exciting from my perspective is that this is actually the transpose. Okay? So can anyone think back to Math 1B? Would you agree that calculating inverse matrices is a pain in the butt? Yes. Yeah, I would too. Maple can do it, of course, right? So it's pretty easy to transpose a matrix. Would you agree? Yeah, like a 2x2 or 3x3, it's pretty easy. So is it easier to transpose or invert a matrix? Transpose. So you want to do that as much as possible. Okay? So this sets you up to not even worry about inverse, you know, determinants or anything like that, right? You just transpose it. Okay? So, shall we have a look at a question and see how it all works? There's a theorem here that we're going to use called the principal axes theorem. Okay, and I'll walk you through it. But if you have a hazy memory of this, or maybe you never learnt it, that's okay. You can put in the missing information. There's enough time to do that, right? So let me just repeat what I said. We're going to look at these forms here, and we're going to do something with them. Diagonal matrices are nice because they're simple. Given some matrix like this, how do you diagonalize it? How do you make it simpler? Well, you form these so-called eigenvalues and the eigenvectors, and you write the eigenvectors as a column. Then you can use P inverse AP, so matrix multiplication. All right? And in these lovely symmetric matricey worlds, or matrix worlds, the inverse of P and the transpose of P are the same. That is brilliant. Okay, that is good. Okay, so let's look at an example. What's happening at home? Switch rows and columns. Exactly. Thank you, Arnav. All right, so let's look at an example. Yep, and I'll just bring up. Okay. This example here is a standard matrix question for this course. Now we will go and use matrices to solve differential equations, but this is just a starting entry level point. Okay? So, consider the following quadratic form. This thing, which is a second order polynomial, equals 6. Okay. Determine the point or the points that are closest to the origin. Okay, now are we having flashbacks to Lagrange multipliers here? Huh? Right, this could be a Lagrange multipliers question. It could be. Can you do it like that? Sure, if you want to. Right? But some of the questions you'll probably get asked is something like this. Write this in this sort of multiplication form, and then do stuff with that matrix A. Find the eigenvectors, find the eigenvalues, right? Through this process, you can finally answer this question, okay? But let's see what makes this problem difficult, okay? Let's see what makes this problem difficult. The first question is, do we recognize this curve at all? It can only be one of two curves. What are the options? When I've got like an x squared and a y squared. Yeah?
Ellipse.
Yeah. What else? So there's an ellipse. What's the other curve with like maybe x squared minus y squared? Yeah, hyperbola. But you can't look at, or at least I can't look at that and go, oh, it's definitely an ellipse, or it's definitely a hyperbola. If I could, that would be helpful, right? Because it's super easy to get the points then. So let's actually draw a picture and see what we've got. Okay, check it out. So it's obviously not an ellipse, but there's no way we could really know that without maybe, you know, using some technology or something. Okay, so who can tell me by looking at the graph what's the answer to our question? What are the closest points to the origin? Oh, it's okay, that's fine. What?
1, -1, and -1, 1.
Yeah. So, you know, you can kind of see now, if you're doing this using Lagrange multipliers, you just blow up a circle until it touched, right? So, as far as I can tell, the closest points are here and here. Okay? Super easy to look at the graph and do it, right? But now, what would happen if we rotate that graph or rotate the axes? Watch what happens, okay? Watch what happens. Have I got it? Yeah. Okay, so I'm going to put in some other information. Oh, why? Why? Boom. All right. So, does it look like those two things are just the same curve, just rotated? Yeah? So, let's go back to our original question. Determine the points that lie on the curve which are closest to the origin. Okay. Well, let's get rid of the original. Can you see how super easy that is? Right? So that's actually what we're going to do. We're going to do it algebraically, and we're going to sort of shift the axes or rotate the curve, or however you want to look at it, until you get something like this. And then it's super, super easy to actually work out the answer to the question. So that's the basic idea. And if you go back to the original question, you can kind of see, okay, well, let's just think of this. There's an axis going through there, and there's an axis going through there, right? So you can see there, it's just a rotation of the original axes. There and there. Okay, so that's actually what we're doing. That's actually what we're going to do. Okay? So, the question is, how do you do it? How do you do it? Okay, so the solution method and the strategy for these questions are usually the same. If they've got it, even if they've got some sort of differential equation in, which I'll show you in week 7, it's still the same procedure. Okay? So we're going to use the stuff that I showed you over here. All right, we're going to use that information. Okay, so how do we do it? Glad you asked. So the first thing I'm going to do is I'm going to write this left-hand side as something like this. And then I'm going to do some analysis on that matrix A. And the matrix A is going to be symmetric. So its transpose equals itself. And that means there's nice things for the eigenvalues and the eigenvectors. Okay? So how do we write this in terms of this? Well, let's see. Okay, so x, y. All right, so for this one, I'm taking the coefficients of the squares and writing them down the main diagonal. Then I'm taking half of the other coefficient and writing it down the other diagonal. Okay? So, is this matrix symmetric? If you swap the rows, the corresponding rows and columns, do you get the same thing? Yes, that's a good sign. Okay? So if that's the case, all the eigenvalues are going to be real numbers and they're going to be distinct. I think we can conclude that. All right, so let's actually compute them. You probably haven't computed an eigenvalue or an eigenvector lately. Let me know if you have, especially everyone at home. Right? So I'm just making a mental note of that. All right. So let's work out okay, so when I'm talking about the word orthonormal here, I'm meaning each of these vectors have length 1 and they're mutually orthogonal to each other, right? So the dot product of v1 and v2 would be 0. Okay, so how do we get these things? Well, let's compute the eigenvalues first, and then we can go on and compute the eigenvectors. So let's make a little note. Okay, so we look at A minus lambda I. Okay? Or you could have lambda I minus A. It's up to you. Okay, you're not wrong. So let's work out the determinant of this thing. So here's A, and we want to take away lambda times the identity. So it's going to be 1 minus lambda down the main diagonal, and nothing else changes. Okay? So remember, with determinants, you work in a sort of diagonal way, so this times this minus that times that, or let me do this for everyone at home. This times this minus that times that. All right? So all right, so we've got a quadratic equation which we can solve, and we're going to get two real values all right, so we're on our way. Okay, there are our two eigenvalues for A. But what we really want is the eigenvectors, because we want to get this matrix P that diagonalizes everything and makes things as simple as possible. Okay? So to get the eigenvectors, we solve the following. Okay? So this is like a linear system down the bottom. Yeah? So there's two cases to consider. Lambda equals -1 and lambda equals +3. So we do them separately. And then each one will have a corresponding vector answer. Okay? So let's do that. All right, so let's go in here and replace, well, actually, you can just go up here and do it. So 1 minus -1, that'll be 2, that'll be 2. Okay, so now it's like a little game to find the components of the vector that you don't know. So what are we going to get? V1 equals V2? So we just choose the simplest case. Let's choose V1 equals 1, V2 equals 1, and then normalize it, right? So our first eigenvector, something like that. Let's normalize it. Divide by its length. Okay? Now for these problems with symmetric matrices and orthonormal P matrices, you want to normalize here, otherwise it's not going to work. Okay? All right, so let's solve the other case, lambda equals 3. All right, so let's go up here, 1 minus 3, 1 minus 3, so I'm going to get negative 2, negative 2. So it's very similar to the previous case, except I've got V1 equals negative V2. Okay, so let's form a vector out of that. So let's say 1 and negative 1 and then normalize it. And then we're just going to write our new vector, our new matrix P with these two things as the columns. Then we're almost done. Okay. All right, so we're feeling good. We're feeling good. Okay. All right, so we've got something, but we're not quite sure what to do with it. So let's move on and see what we can actually do regarding this original form. Okay, so this is quite interesting. So let me see if I can show you how we do it. So I'll just squish it in down here. All right, so here we go. So this is my original quadratic form. Yeah. Okay, so note that up there. All right, so now, because this diagonalizes P, diagonalizes A, I can write it like this. Now you don't have to do all this working, but I'm going to just put it in for completeness. Okay? So basically, because P diagonalizes A and P transpose and P inverse are the same, I can replace A with that mess. Now I'm going to tease it out a little bit. Okay? I'm going to use the properties of the transpose. And you'll see what happens. Okay? So, we don't know what this D matrix is, but actually we kind of know what it's going to be. It's going to be the diagonal matrix with the eigenvalues down the main diagonal. But let's see what happens with this, okay? Because it's kind of interesting. Let's see what happens. So let's just compute these things and see what actual expression we get, because we're going to turn this into something much nicer, okay? So I'm carrying on this equal sign down here, all right? So transpose of that times that and transposed again. So let's just see what happens. So that's there. I'll transpose that to get P transpose. So you can see that yeah. Yep, that doesn't change, which is good. Okay, so I've done that. I'm going to do the transpose in a minute. The diagonal is just the matrix with the eigenvalues down the main diagonal. And then what's this? Okay, well, let's do the transpose of that and multiply it. Okay, so it looks like a bit of a mess, but remember we've got hope here because this diagonal matrix is going to simplify things massively. Okay, so just bear with me because I know it looks like we've made it more difficult. But let's simplify. Let's do this calculation and we'll take the transpose in a minute. And over here, x plus y, x minus y. Okay. All right, we're almost done. I know it's been a long road. What do you notice about the two vectors here? They've got the same sort of format, x plus y, x minus y, x plus y, x minus y. Okay, so let's do something with that. Let's form a transpose. So I'm putting the root 2 back inside because something magical is going to happen in a second. Okay? If we expand this, what are we going to get? Well, negative times that, 0 times that. Let's do it and see what happens. If you expand this, what are you going to get? Okay, now, that tells you basically a lot about the original curve. It's just in the new or the transformed axes. Okay, so if you don't like the look of that, let's just introduce a new variable, or two new variables. Right? Okay? So who can tell me, just forget about everything else, if you're in the y1, y2 plane, that's pretty easy to draw, right? It's a hyperbola, and the principal axes of that hyperbola will be the y1, y2 axes. Yeah? So it'll actually look, in the new setting, like this. Just put it up on my computer. Boom. The horizontal axis is big Y1, the vertical axis is big Y2. Okay? So it's pretty easy if you can draw it in the new set of axes to actually answer the question. What's the closest point? Well, it's on one of the axes in the picture, right? It's where the 2 points where the curve cuts the axes. So that it's sort of a general theorem called the principal axes theorem, right? So just by changing the variables or making a substitution, we simplify the situation. And does anybody remember the method completing the square in algebra? Completing the square. Anyone? This is a generalization of completing the square. So maybe you saw it at school, you know, that's okay. Maybe you use it. Oh, you've come just at the right time. Yeah. Are you ready for a break next week? Yes, I think we all are. So, okay, so I've got a question for you. Which is the simpler curve? That's that situation, or you've just walked in, so this would be a good question. Or that situation. I would say so as well. I think to me that looks simpler than something that's not quite sort of symmetric about the axes. Would you agree? I would agree. Right? Yes.
What's y1 and y2 visualizing?
The axes.
I don't see that.
So I'll tell you exactly what y1 and y2 are. It's in the algebra, right? So you can think. Let me put this up for everyone at home, because it's a good question. You can think of y1 being this bad boy here, and y2. So it's a change of variables. Change of variables. Okay? And what does this mean for, let's say, for our eigenvectors and eigenvalues that we spend a lot of time calculating? Well, I'm glad you asked. These are the eigenvalues, and the eigenvectors point in the same direction as these axes. Okay? So if I was to go back to my computer and show you that. There's one vector, that's one eigenvector pointing that way, and there's another one pointing that way. So the eigenvectors that you're computing lie along the new set of axes that you're sort of rotating or transferring everything to. Okay? There's quite a lot to take in on a first sort of viewing. So how's everyone going at home? Let me know. Oh, okay, yeah, good question. This used to upset me all the time when I was at uni. Right? I used to get triggered and, you know, have a tantrum and stuff. Okay. People freak out when they need to solve these sort of equations. Okay? Because it's not clear how you go from this to this. Yeah, so basically the first line says 2v1 minus 2v2 equals 0, right? So you know v1 equals v2 for this case. Yeah? So how many solutions are there for a case like that? If v1 equals v2, how many different v1s and v2s satisfy that? Yeah, infinite, right? So you have to make a choice. You can choose any v1 and any v2 as long as they're the same. So you could choose v1 equals 100 as long as you choose v2 equals 100. Okay? But why is that problematic? Well, if you're going to normalize everything, right, you're going to have a pretty nasty looking square root down here. So I try to keep things as simple, because I'm a simple dude, right? I try to keep things as simple as possible. Okay? So for this one, you want to choose v1, so it's the negative of v2. I've chosen v1 equals 1, so v2's got to be negative 1. Who can think of another choice in the second case for v1 and v2? Who can think of another potential vector or answer or whatever? Yeah?
2 and minus 2?
Yeah, v1 could be 2, v2 could be negative 2. What about if we smash the system and do something radically different? Yeah. So hang on, this is good. I'll pass the mic.
-1 and 1.
Yeah. So you could say, oh, I'm going to choose v1 to be negative 1. And then v2 has to be the negative of that. Okay? All right, there's a question at home on the chat. Let me bring that up. People are going, oh, I thought I'd given eigenvectors, eigenvalues away. In your engineering courses, are you ever calculating eigenvectors or eigenvalues? Not yet. Probably never, but maybe. Who knows? Who knows? Right? Internal computer. Okay. So hopefully I've explained that second bit, and I'll give you a little thumbs up. Thank you. Switch rows and columns, yeah. All right. So will your eigenvectors that determine your new coordinate system always result in allowing a nice plot of the graph? Yes. Yes. And do you know why? That's a brilliant question. No, it wasn't just luck. Okay? Okay, let's do some unmasking here. Julian, you rule. Okay, sorry, it's a good question. I want to give you your props. Okay? It's not random, right? So if the form here that we got so I've just added that line down the bottom, which you can't see. Yeah. So what could that be? What kind of graphs could this bottom line be in the y1, y2 plane? Well, if lambda 1 and lambda 2 are positive, what's it going to be? An ellipse, right? Yeah, assuming you've got a positive thing on the other side of the equation. And if one of them's negative, it's going to be hyperbola. Okay? So we know that these nice matrices are only going to give us real eigenvalues, and they're not going to be the same, so we're not going to get a circle. I don't think we're going to get a circle. And from that bottom form, we can say, hey, it's either an ellipse or it's a hyperbola, depending on the signs of lambda 1 and lambda 2. Okay? So to answer your question, Julian, at home, it's a good question. It's not luck. And all the questions that you see will be like this. Okay? But you've got to know your eigenvalues. You've got to know your eigenvectors. Need to be able to diagonalize, right? Like I've put the working in for this one because I wanted to show you the actual relationship between the variables, right? There and there, there and there. Most of the questions in this course, they don't care. They just want you to answer, oh, where's the closest point to the origin? Okay, so should we actually work that bit out? Let's do it, right? So let's actually do the thing we wanted to come to do, all right? So in this, let's have a look. Go back to our thing, okay? Where does it look like the closest points are? It's sort of at, you know, it's not 1, it's not 2, it's actually going to be square root of 2 and then negative square root of 2. Okay, if you're worried about that, just put in go into the original transformed equation, put in x equals 0 and solve for y. It's going to be positive root 2 and negative root 2. Okay, so let's go back. I'll put that one up there for everyone. Okay, so now we want to get that back into the original coordinates. Okay, the original coordinates. So how can we do that? Well, in this situation, we can use our matrix P to get us back. Okay, so our matrix P was, where are you? There, and we just multiply that by these points here. Yep. Okay. So what are we going to get? Oh my goodness. We should get that point there, and that point there, right? 1, -1, and -1, 1. And in fact, if you look carefully at the multiplication, that's exactly what we're going to get. So they are the two closest points in the xy plane that are on the curve and they're closest to the origin. Whew. Now I've shown you everything, pretty much everything there. When you're doing these problems, you don't need to give all that information, right? All you really need to do is write down the form by computing the eigenvalues, right? So you get these eigenvalues first, right? Write this down depending on whether the sign is positive or negative. You'll either have an ellipse or a hyperbola. And then when you want to find the original points, boom, that's it. Okay, now what else can you tell from this picture? I've put both graphs up there now. When you rotate, does it change the distance between the graph and the origin? Does it change the answer in terms of the closest point or the shortest distance? It doesn't. It doesn't. So it changes their position, but it doesn't actually change the distance, right? Yeah. Yeah, no, that's okay. That's okay. So with these things, it's all about rotation. It's distance preserving, right? It doesn't change the distance. And you can solve these problems using matrices, okay? So let's take a break. I've gone 2 minutes over. We'll come back in 10 minutes. And that's it's the last lecture before week 6. Does anybody have a class after this? All right, we'll make it fun. All right, so see you in about 10 minutes. Good question from home. We would only use this for like distance questions. Yeah. Yep. But we'll also use this method for solving systems of ordinary differential equations. Okay, so I'm not going to talk about that today because it's too overwhelming. But we will use this to solve, a whole bunch of, basically linear systems, but with derivatives. Okay? Who was that? Julian again. You're on a roll, man. Okay. So I was thinking that we could do some of the Mobius questions. We okay with that? Yeah? Makes sense. Also, who's regularly going to tutorials? Who's regularly going to tutorials? Yeah, okay, good. Good. I was at the pub last night with one of the tutors, and he sort of revealed to me that he's getting a class of 4 people turning up. And I'm looking around and I'm like, oh, is it? No. He said it's all quality rather than quantity, right? Yeah. So, but then again, look around, like this would be a small tutorial class, right? So, it's not necessarily a bad thing. Oh. All right. So I thought we could work through a couple of these questions. Let me have a look. I'm going to do, so let's talk about this. So I showed you this, I think, earlier in the week, and it was the variation of parameters, aka variation of constants, okay? And for this one, it's a bit smudgy. Is that better? Maybe a bit better. For this one, you are given it in your lab test too. Okay, so you don't need to remember it, you just need to apply it and know some of the tricks, right? So I thought we could do some questions involving that today. Okay, so let's just refresh our memory. It's all about the homogeneous. Okay, it's all about the homogeneous problem. You get two linearly independent solutions to the homogeneous problem, and then in that red boxed form, you do stuff with those two bits. You integrate and you get a nice form. And the Wronskian is defined in this way. It's like a determinant, and basically you want it to be non-zero. And for all the problems that you'll see, it's always non-zero. Okay? Okay. So let's do a couple of questions. Come back to you. Where are you? Just give me a second. Oh! Yeah, all right, this is a good one. Variation of parameters. Okay, so you can see they give you the format for a particular solution, and you're given the Wronskian, and you're given a differential equation. Okay? So, with these ones, the method is usually the same. In fact, I would argue it's always the same. We solve the homogeneous problem, and then we do stuff with the parts of the homogeneous problem. Okay? So, let's start. The characteristic equation for this one is going to be lambda squared minus 6 lambda plus 9 equals 0. Okay? So let's see if we can find lambda, and the form of lambda will tell us our parts to our homogeneous solution. Okay, so we can factorize that. So in this one, we're going to get two solutions, two repeated solutions, and they're both real. Okay, sure, no worries. So with this one, what would our general, what would the two solutions be that we want to sort of work with in this? Who can tell me? We've got real values for our characteristic equation solution, and they are equal. So what should we write down for our solution? Our solution to the homogeneous problem. Come on.
Would one be e to the 3x and x e to the 3x?
Yeah. So that's what you were going to say too, right? Yeah, good. So let's try y1 equals e to the 3x and y2 equals x to the 3x. Now, on Wednesday morning, somebody says, why is that x there? Why is that extra x there? And I tried to explain it, but I could tell this student wasn't very impressed, right? So I went home and I thought about it. And I was like, oh, turning in my sleep, going, how am I going to answer that question? Okay, so why do we have these solutions? Well, this one's pretty easy to explain because you want a form that doesn't change much when you differentiate it. And it's the same with this. This doesn't change much when you differentiate it. Okay? So that was the best that I could come up with. So hopefully that's okay. Right? All right. So now let's use let's use that information. Now, Julian, is this you? Ah, Aliyah, hello. Would there be questions involving 3 variables? Yes. So for the matrix stuff, yes. So instead of 2 eigenvalues, you're going to get 3. Instead of a 2 by 2 matrix, you're going to get a 3 by 3 matrix. Okay? So yes, there will be. All right. Well, it's going to be a surface, isn't it? A surface, okay? So what I'll do is, in week 7, I'll show you some surfaces, and we can classify them, okay? So it'll be like a hyperboloid or an ellipsoid or something like that, right? Think of the 2-dimensional versions of an ellipse. Well, it's like a sphere, but it's not all round all the way over. Okay. All right, back to our revision. 2 functions that solve the homogeneous problem. Let's do it and see what happens. Before we do that, though, let's calculate the Wronskian. Okay. So, Wronskian. Okay, y1 times y2 dash minus y2 times y1 dash. Okay, so this involves us taking some derivatives here. The e to the 3x is fine, but the x times e to the 3x is not so nice because it's a product rule. But let's try. Let us try. Okay. So y1 times the derivative of that. Okay, it's going to be 1 plus 3x e to the 3x. Okay, I think that's correct. Yep. And then minus y2 times y1 dash. All right, so that times the derivative of that. Okay, so I've got a bit of a mess, but things are going to cancel out. Okay. Okay, so I've got some nice cancellation there, and I'm left with, I think, e to the 3x. Yes. Phew. Okay. So now let's take those parts, put them into the y sub p formula up the top. Okay? Now, notice they only ask you for y sub p in the answer. They don't care about the solution to the homogeneous problem. Okay, so you could write down the solution to the homogeneous problem, great, no worries, but it's not necessary. Okay, you just need to know the parts. Okay, so let's do some integration. Okay, y sub p. Okay, I'm gonna, so a is 1 here, so I can just forget about putting anything down there. Okay, so this is your f. Yeah. And so we just need to go through and multiply and, simplify and do all that sort of stuff. Okay. So y1's that, so it's going to be negative e to the 3x times this integral, x times that, all over the Wronskian, which is that. Okay, so it looks a bit messy, but the exponentials are going to cancel. Okay, which is good. Okay, so they're going to cancel, and then it's this one here. So y2 is that. Wij van zat. Sorry, e to the 6x. Okay, so that's going to cancel. Boom, boom, boom. So the second integral's easy. The first integral, you've got to do integration by parts. Okay, x times cosine x. Unless you know a quick way to do it. Okay? So, do integration by parts here. So let's just move things around and make it look a bit easier. Yeah, I'm going to, ooh, yeah. Thank you. Okay, so that's really what we're looking at now. The second integral is going to become sine of x. The first integral, you can do integration by parts. Okay? Okay? So, if you integrate by parts, this is what I got as my final answer. Okay? So, a good question here is if you're doing this, does it matter with integration by parts? What should my choices be for integration by parts here? Anybody know? So I want to choose u and I want to choose v dash as parts of my integral. Is there a strat that we can use?
Because we see that the x is kind of annoying us, we treat that one as the differentiated like u, and the cos x as v dash.
Yep, that sounds pretty good. So in this situation, sometimes I find them both annoying, by the way. So I would let u be x and v dash be cosine x, right? And the idea is that if you differentiate u, you get something simpler. So 1 is simpler than x. Yeah? And if I swap my choices, I'm not going to make it work, really, because I'm going to make things more difficult. Yeah? Okay? Questions? Okay. Questions at home? All right, 14 people are still hanging on. Let me know what you're doing at home, by the way. How are you sort of listening to the lecture or watching the lecture? Let me know what's going on. All right, questions? That's a pretty standard problem. The Wronskian was not a constant, right? W was not a constant. It was e to the 6x in this situation. And what you would hope is it would cancel out, right? And it did, which is great. Okay? It did, it was great. Okay, so let's play a game. Come on, people, I'm staring at the screen, waiting for your response from home. I want to know what you're up to. Okay, let's... Ooh, yes. This is a good one. Hang on. Is this... Oh, this is the one that I just did. All right, so I'm going to do this a slightly different way now. Or is it? No, no, it's not the same one. It's similar but not the same. Okay, so remember earlier in the week, I showed you an annihilation method for differential equations. Basically, you annihilate the differential equation, so you basically smash the right-hand side to make it 0. Okay, so, you can smash that through differentiation until the right-hand side is 0. Does anybody remember this? People were like losing their minds. They're like, why don't we know this? Is it a genuine technique? And I'm like, yeah, right? So here's a game that we can play. With this question, they want you to use the standard first year techniques. Okay, you could use variation of parameters, this new method that we learned. Is there another way? Is there another way? So, here it is. What would you have to do to this equation to smash the right-hand side to 0 through differentiation? What would you have to do? What's something you can do to smash the right-hand side through differentiation to make it 0? Have a think about it. It's not an easy question. I will tell you this, it is possible. It is possible. Okay? What can you do to that star differential equation through differentiation to smash the right-hand side to 0?
Differentiate it not in terms of t?
Yeah, that would work, but something with respect to t. So, yes, that's technically what you're saying is true, and I have no problem with that, but I'm trying to do something with respect to t there.
Make t equal to pi on 2?
But we can't fix t because it's the variable, and we want it to hold for all values of t. So one value would make it work, yeah, but not exactly. Okay, all right, here we go. Round 2.
Set t equal to something else and then differentiate in terms of t?
No. I like it though. I like it. I like the mindset. It's very good. It's very good. Well, let's do something. Let's do something, right? Let's just try something. What happens if I differentiate this with respect to t? Just the right-hand side. What do I get? Okay. And what happens if I differentiate it one more time? I'm back to cos, right? And I've got a negative sign in front of the cos, right? So, what happens if I differentiated both sides twice and then took the original thing away from both sides? What am I going to get? I'm going to get 0 on the right-hand side. Okay? So you can do it. You can do it, right? So let me see what I've got written here. Oh, yeah. So let's say I've got L, Y. So think of L as a linear operator, right? Just a differentiation operator. Yep. And then I can say, okay, my, I'm going to define it to be, what am I going to define it to be? Yeah. Is that right? Yeah. So what I'm going to do is I'm going to go up here, differentiate both sides twice, and then add 9 lots to it, to both sides. Okay, let's see what happens. All right, so I'm starting with this. I'm going to differentiate it twice and then add 9 lots of both the left-hand side and the right-hand side to both sides. Okay? All right, so that's the left-hand side when I'm applying this. That's the right-hand side. Okay, so let's actually do it. Okay, that's the left-hand side. Okay, so the right-hand side, if you expand this, you differentiate twice, you're going to get something like negative 270 cos 3t, and you add 270 cos 3t in there, the right-hand side's going to be 0. So what are we going to get? Well, we're going to get something like this. That's going to be y to the 4th. You're going to get 18 y double prime plus 81 y equals 0. So congratulations, everybody. We have a homogeneous problem now. We have a homogeneous problem. So what do we do with homogeneous problems? Characteristic equation. Yeah? Characteristic equation. So what's the characteristic equation for this mess? Well, it's going to be lambda to the 4 plus 18 lambda plus 81 equals 0. Now, squared. That looks a bit difficult, so let's make a substitution. Okay? So we know how to solve that. It's going to be like 9 and 9, something like that. So, yeah, negative 9 and negative 9. Okay, so when we went from here to here, I made the substitution. Yep. So let's take the square roots of those things. We're going to get positive and negative 3i. Okay? So what do we do when we have complex roots? What are our functions for, first year problems? What? Sine and cos. But we've got repeated roots. We'll do t's, okay, because it's a function of t. All right, so you can say the solution to this problem bump, bump, bump. Okay, so that's your general form. Now, if I was doing this in an exam, would I solve it this way? No. You can if you want, but I wouldn't do it, okay? So all you need to do to solve this problem is find that value and that value, right? And you do that by putting this okay. So what did I get? Did I do it? I think I did it. Hang on. Yeah. So C equals 5, D equals 0. All right, so what's the format of the particulars? Here's y sub p, by the way. Okay, so y sub p is going to be 5t cos 3t. Okay, I've left out some of the algebra, but that's the answer. Okay. Questions? Could you use first year techniques there? Of course you could. I would probably recommend you use first year techniques. But this is a nice technique because it tells you where the forms come from, right? It tells you where the forms come from. Questions, comments, observations? So, let's see, 13 people. What is everyone doing in week 6? Oh, thought I just asked it. Let me know. Huh? What? How do I post it? I'm trying to engage so hard. Oh, there it is down there. Okay. Oh, let's post anonymously too. So one thing I've noticed, there's very little student-to-student chat on the live stream. During COVID, it was like a torrent. It was like a Twitch torrent, right? Like people were saying all sorts of stuff. But yeah, it seems pretty quiet now, right? Golf. Good job, Sam. Excellent.